This is a continuation of the example problem on a two-pole grid-tied inverter. In part 1, we looked at the power flow from the DC side to the AC grid. In this video, which is part 2, we will analyze the case of reverse power flow, that is power flow from the AC grid to the DC. We will do this using the same phasor analysis, and in this video we will have time to go through the detailed phasor diagram and the corresponding time domain average quantities. Okay, here is the problem statement. We are given a two-pole converter that interfaces a DC voltage of 450 volts to a single phase AC grid of Vg equals 340 sine 377t 60 Hz. And we are also given that the total filter inductance on the AC side is 2 millihenry, and the resistance of this filter inductor is 0.1 ohms. And the problem requirement is to calculate the control voltages for the two legs, VCA and VCB, for the two cases below. So in part 1, we looked at the case of 5 kilowatt of power flow from the DC side to the grid at some 0.866 power factor. And in this video, our focus is going to be on calculating the same control voltages, VCA and VCB, for the case of reverse power flow of same active power 5 kilowatt from the grid to the DC. And in this case, we want the power factor to be uniform. Okay, to quickly recap what we did in part 1 of the video, which is the analysis of the power flow from the DC side to the grid. So what we did was we drew the average model first, that is shown here, and then we used KVL in the secondary side, and we used phases for each of these voltages and currents. So we defined the grid voltage as our reference phasor, so that is 340 angle 0 degrees. Then we calculated first of all the grid current for the given power requirement and power factor requirement. So the power in a single phase is given as this expression, Vg peak Ig peak over 2 times the power factor cosine theta, and from that the current comes out to be 33.96 amperes peak. And given that the current lags by 30 degrees, so the complete phasor for the grid current is 33.96 angle minus 30 degrees. Then we can calculate the two voltage drops across the resistance and the inductance. So VR is simply R times the grid current Ig, and so it's 0.1 times the grid current. VL is J omega L, its impedance, times the grid current, and that comes out to be 25.6 volts peak with an angle of 60 degrees with respect to the reference, which is the grid voltage. Then we can get the VAB phasor as the sum of the grid voltage Vg, VL and VR all in phases, and that is written here. And VAB sums up to be 356.33 volts with an angle of 3.295 leading with respect to the grid voltage. And from that we can calculate the control voltage as a phasor, which is simply VAB over the DC link voltage 450. So that comes out to be this value, this phasor, and the corresponding time domain expression for the control voltage Vc of t is the same magnitude as the peak, 0.792 sine 377t, and this phase angle of 3.3 degrees roughly. And once we know Vc, then the control voltage for leg A, VCA, is same as Vc, and that for leg B, VCB, is negative of Vc. Okay, the main reason that I went through this recap of the previous case is to actually show each of these main quantities in a common phasor diagram, and also correlate those phasors with their corresponding time domain waveforms. Now this analysis gives a much deeper intuitive understanding of exactly how the two-pole inverter operates in steady state. So let's start with our reference phasor, the grid voltage Vg. As a phasor, it is 340 volts angle 0 degrees, and that is indicated by this line. So the length corresponds to the magnitude, and the angle, so here is our this is our reference axis. Okay, so the Vg is aligned with the reference axis. Now the corresponding time domain waveform is shown here. So in this case, the grid voltage is a pure sinusoidal, so it's instantaneous, as well as the average value, cycle by cycle average value, is still this sine wave 340 sine omega t. The peak is this peak is 340 volts. The next phasor is the grid current IG. As a phasor, it is 34 amperes, angle of minus 30 degrees. So this angle is is 30 degrees. And in time domain, it is another sine wave. It lags the grid voltage by 30 degrees. So you can see, so this is 90 degrees, this is 180. So therefore, this is exactly 1/3, 30 degrees. Okay. And the peak value here is 34 amperes. Actually, the scale for the current is on the right, so this is 34 amperes, and all the voltages, so every quantity except for the grid current, they are all voltages, and they have the left axis scale. Now, in fact, I should call this as really IG average of t, because only then it will be a perfect sinusoidal signal. The instantaneous IG will have some high frequency ripple. It's not a pulsating waveform. It is more or less a smooth waveform, very similar to what is shown here in blue, but it will have a small high frequency ripple on top of this. But of course, in phasor analysis, so in this phasor, this only corresponds to the fundamental component of IG. Okay, the next phasor is the VR, the voltage across the resistance, and actually I showed this is not so small, it's barely visible. It is right here. I will do it again. So I removed it, and there you see a small arrow here. So that is VR, and as you would expect, it is in phase with the grid current, the resistor current, and VR as a phasor is 3.4 volts with an angle of minus 30 degrees, same as the current. And the corresponding time domain waveform is shown here, this green waveform. That is actually a sinusoidal waveform. It is hard to see because its magnitude is just 3.4 volts, and in a scale of 400 volts it is hardly visible. The next quantity we will see is the phasor VL, the voltage across the inductor, and as a phasor it's 25.6 volts, angle of 60 degrees. So this is the inductor voltage, so it leads its own current, which is same as the grid current, by exactly 90 degrees. So VL leads IG by 90 degrees, and the corresponding time domain waveform is shown here. So you can see the brown waveform is the inductor voltage and leads the current. So this is VL, and this is IL or IG, and you can see the brown waveform leads, the peak is here and the peak for the current is here. So the VL leads the current by 90 degrees. Now here it's quite important to emphasize that VL of t, so again I should clearly show that this is the average quantity, same as IG is also average. So VL instantaneous is a very different looking waveform. It's you can hardly make out the sinusoidal component, but in our analysis, in our phasor analysis, we are dealing only with the fundamental component of VL, removing the switching frequency component, and then the phasor would be as shown here, and this VL average is as shown here. Okay, then adding the VR and VL phasor to VG. So that's VG plus VR plus VL. I just took the VR and VL from here and put it at this point. So there's sum VG plus VR plus VL is equal to this VAB. Okay. And so the VAB phasor is a magnitude of 356 volts with an angle of 3.3 degrees. So this angle here is 3.3 degrees. Okay, then the corresponding time domain waveform of VAB is shown here. That is this black sinusoidal waveform, and this can also be obtained by the addition of the instantaneous VG, VL, and VR. So that will come out to be this peak value of 356 volts, and it leads the reference phasor, the grid voltage, which is the red waveform, by 3.3 degrees, and that can also be seen here. It's very close, but it is a leading waveform with respect to the red waveform. And finally, I show the control voltage VC as a control signal, so it is not to the same scale as the VAB voltage. So VC has a magnitude of 0.79 and angle same as VAB. So if we apply the corresponding time domain waveform, which I'm not again plotting here, it will be hard to see in a scale of 400 volts. But if you apply this 0.79 volts sine omega t plus 3.3 degrees, then we'll get the corresponding lagging current and the 5 kilowatt of power flow. Okay, and finally I also want to emphasize again the the instantaneous quantities versus cycle by cycle average and the fundamental component that is used in the phasor analysis. So as an example, this green waveform, that is the instantaneous VAB, that is switching from 450 volts to 0, and here it is switching between 0 and minus 450, the DC link voltage. And if I do the cycle by cycle average, then I get this waveform. Inside that, this the blue waveform, okay? And that is the this blue waveform here, that will be VAB, the cycle by cycle average quantity. And the top plots show the red waveform is the grid voltage VG of T, and the upper waveform is really the fundamental component of this VAB. It's very close to this cycle by cycle average value. And we can also look at the Fourier spectrum of this VAB instantaneous as well as VAB average, and that is shown here. And I'm only focusing on frequencies up to looks like 1200 Hertz. So this is voltage in volts, and this is frequency in Hertz. The blue waveform is the cycle by cycle average, and the green waveform is instantaneous. And certainly at low frequencies they have the same frequency content, and will be quite different at switching frequency and its multiples. So let's look at the magnitude at 60 Hertz. Okay, that's 60 Hertz at this point. Okay, so both the instantaneous and the average, they have this magnitude here is actually 356 volts, the magnitude of the VAB phasor. Okay, and only this component is used in the phasor analysis. Okay, so that brings us to the case 2, which is a reverse power flow of 5 kilowatt from the AC grid to the DC voltage source and at unity power factor. Now the analysis method is going to be identical to the case 1, just that the numbers would be different, corresponding to the different power flow direction and a different power factor. So we will start with the cycle by cycle average model. The model itself, as well as the all the assigned current directions and voltage polarities, they are exactly the same as the case 1. Just that the power flow will be, instead of 5000, it will be minus 5000, and we can use that to calculate to begin with, to calculate the grid current. Okay. So once again, that is the expression for power in a single phase system, and PG in this case is minus 5000. Therefore, and also the cosine theta here is 1 for unity power factor. There is this 1 here, okay. And the peak voltage is again 340. So that leads to a current of minus 29.41 amperes. It's minus because of the reversed power flow direction. And similar to case 1, we will again use the grid voltage VG as a reference phasor. So that's a time domain expression, and the corresponding phasor is 340 angle 0 degrees. Okay. Then the current phasor, it has a magnitude which is calculated 29.41, and the angle is 180 degrees, plus or minus 180 degrees amperes. Okay, so we have our VG reference phasor and the current phasor. So let's go ahead and calculate the other two voltage drops, the resistive and inductive drop. VR is R times IG, and R is just 0.1, so it's going to be just 0.1 times this value. So that's 2.94 angle 180 degrees, and VL is J omega L times IG, and omega is 377, L is 2 millihenry. The current magnitude is 29.41, and the angle would be the current angle, which is 180 degrees, plus a 90 degrees introduced by this term J. The VL leads its current by 90 degrees. So that leads to VL phasor to be 22.2 volts and an angle of 180 plus 90, which is 270, same as minus 90 degrees. And finally, we can add the VG, the two drops VL and VR, to get the required VAB to be delivered by this two-pole converter. So VAB as a phasor is VG plus VL plus VR, and that comes out to be VG is simply 340, and VL, so this is same as minus J 22.2, that is here, and VR has only well, VR is also is the same as minus 2.94, so that is indicated here. Okay. So then VAB comes out to be 337.78 volts with an angle of minus 3.764 degrees. Okay. So once again, as a check, that the power flows from the source that has the leading phase angle to the one which is lagging, and in this case the power flow is from the grid to the two-pole converter, actually to this VAB source, and then eventually to the DC source. So we expect VAB to be lagging with respect to the grid voltage, and that's exactly what we get here. Okay, then the control voltage as a phasor can be obtained by dividing VAB phasor by the DC link voltage 450 volts. So VC is VAB over VD, and 337.78 over 450 is 0.751, and it has the same angle as VAB. And finally, in time domain, VC of t is 0.751 sine omega t minus 3.764 degrees. And in a two-pole converter in this switching model, the control voltage for leg A is same as VC of t, and control voltage for leg B is minus 0.751 sine omega t minus 3.76 degrees. Okay, so what you have seen is just by changing the control voltage very slightly. So if you looked at the control voltage for the case 1, it was 0.7, probably 0.79, and the phase angle was slightly leading, about 3.7 degrees positive. Just by changing that to 0.751 and angle to minus 3.7 degrees, we go from a positive 5 kilowatt from the DC side to the grid to just the opposite, 5 kilowatt taken from the grid and fed to the DC. In a later video, we will look at the complete simulation of this example for the various operating conditions, and that will completely validate our analysis and also give us an opportunity to look at the various waveforms, the instantaneous and the average waveforms. Okay, then as in case 1, let's also go through the complete phasor diagram and the corresponding time domain waveforms, but this time corresponding to the second case of reverse power flow at unity power factor. So again, as before, our reference phasor is the grid voltage 340 angle 0 degrees, and the corresponding time domain quantity is this 340 sine omega t. Then the grid current in this case is exactly out of phase with the grid voltage because of reverse power flow at unity power factor, and the corresponding time domain waveform is this sine wave with a peak of 29.4 amperes. The scale is to the right, and as you can see, this is exactly in phase opposition to the grid voltage. Then this small waveform here, that is the VR of 2.94 volts, and again it's in phase with the grid and totally out of phase with the in phase with the grid current, and exactly in phase opposition to the grid voltage VG. And the corresponding time domain waveform, again this is a small sine wave in phase with the grid current, the blue waveform, but it's not clear to see because of the small scale. Okay. The VL, the inductor drop, is this waveform. Again, it leads the grid current or the inductor current by 90 degrees, as you can see, and the time domain waveform is this brown waveform. Okay. Once again, if you compare the brown waveform with the blue waveform, the brown peak is here and the blue peak is here, and this leads the current by 90 degrees. Then let's add VG, let's add VR and VL to VG, and you will get our required VAB. So this is VG phasor 340, VR is subtracted, it is exactly out of phase, and VL is this waveform, and that comes here, and the sum of these three phases is the final VAB phasor. That has a magnitude of 338 volts, and the phase angle is minus 3.8 degrees, as we would expect for the reverse power flow condition. Okay, then the corresponding time domain waveform is this black waveform. Let me show it again. So that is it should have a peak of 338. So the black has a peak of 338, and as you can see from here, the black waveform, which is VAB, is slightly lagging the grid voltage, which is the red waveform, as again needed based on this phasor analysis. And finally, the control voltage VC is going to be in phase with VAB, and its peak value is 0.75. This also is a sine wave, 0.75 sine omega t minus 3.8 degrees, and that is I'm not showing that waveform because that will be hard to see in this scale of 400 volts. Okay, and finally, I just wanted to give a quick comparison of the phasor diagrams for the two cases that we have analyzed. So first case is power flow from the DC side to the AC grid. Second case from the AC to the DC side. Okay, and the main thing to note is you can see the currents are different based on the problem statement, the requirement on the power flow. But the main thing that I want to show was this control voltage VC is it's kind of very close. This 0.79, this is 0.75 amplitude. The phase angle, of course, is 3.3 degrees positive for power flow from the DC to the grid side, and when the power flow is reversed, we expect the phase angle of VAB and therefore the control voltage to be negative. But you can see it is a very small change, and just by this small change, and so is the VAB. It's both have comparable magnitude. Phase angle of just 3.3 degrees, phase angle of minus 3.8 degrees. With that small change, we are able to change the power flow from positive 5000 to negative 5000.